Line 9. Other considerations. First section, pre-paging. An obvious property of pure demand paging is the large number of page faults that occur when a process started. This situation results from trying to get the initial locality into memory. The same situation may arise at other time. For instance, when a swapped out process is restarted, all its pages are on the disk, and each must be brought in by its own page fault. Pre-paging is an attempt to prevent this high level of initial paging. The strategy is to bring into memory at one time all the pages that will be needed. Pre-paging the page frames for small files. In a system using the working site model, for example, we could keep with each process a list of the pages in its working site. If we must suspend the process due to an I/O wait or lack of free frames, we remember the working site for that process when the process is to be resumed. Because I/O has finished or enough free frames have become available, we automatically bring back into memory its entire working site before restarting the process. Pre-paging may offer an advantage in some cases. The question is simply whether the cost of using pre-paging is less than the cost of servicing the corresponding page faults. Section 2. Page size. The designers of an operating system for an existing machine seldom have a choice concerning the page size. However, when new machines are being designed, a decision regarding the best page size must be made. As you might expect, there is no single best page size. Rather, there is a set of factors that support various sizes. Page sizes are invariably powers of 2, generally ranging from 12 power of 2 to 22 power of 2 bytes. How do we select the page size? One concern is the size of the page table. For a given virtual memory space, decreasing the page size increases the number of pages and hence the size of the page table. Memory is better utilized with smaller pages, however. If a process is allocated memory starting at a location 0 and continuing until it has as much as it needs, it probably will not end exactly on a page boundary. Thus, a part of the final page must be allocated, but will be unused. Assuming independence of process size and page size, we can expect that on the average, half of the final page of each process will be wasted. Another problem is the time required to read or write a page. I/O time is composed of seek, latency, and transfer times. Transfer time is proportional to the amount of transferred, a fact that would seem to argue for a small page size. However, as we shall see, latency and seek time normally drive transfer time. At a transfer rate of 2 megabytes per second, it takes only 0.2 milliseconds to transfer 512 bytes. Latency time, though, is perhaps 8 milliseconds, and the seek time 20 milliseconds. Of the total I/O time, therefore, only 1% is attributed to the actual transfer. Doubling the page size increases I/O time to only 28.4 milliseconds. Thus, a desire to minimize I/O time argues for a larger page size. With a smaller page size, though, total I/O should be reduced since locality will be improved. A smaller page size allows each page to match program locality more accurately. With a larger page size, we must allocate and transfer not only what is needed, but also anything else that happens to be in the page, whether it is needed or not. To minimize the number of page faults, we need to have a large page size. For example, a page size of 200 kilobytes that used only half of that memory would generate only one page fault with a page size of 2 kilobytes, but 102,400 page faults with a page size of 1 byte. Each page fault generates the large amount of overhead needed for processing the interrupt, saving registers, replacing a page, queuing for the paging device, and updating tables. So the historical trend is toward large page size. Section 3, TLB reach. In Chapter 8, we introduced the height ratio of the TLB. It refers that the height ratio for the TLB refers to the percentage of virtual address translations that are resolved in the TLB rather than the page table. Clearly, the height ratio is related to the number of entries in the TLB, and the way to increase the height ratio is by increasing the number of entries in the TLB. Related to the height ratio is similar metric, the TLB reach. The TLB reach refers to the amount of memory accessible from the TLB and is simply the number of entries multiplied by the page size. Ideally, the working size for page size is stored in the TLB. If it is not, the page size will spend a considerable amount of time resolving memory references in the page table rather than the TLB. If we double the number of entries in the TLB, we double the TLB reach, however. Another approach for increasing the TLB reach is to either increase the size of the page or provide multiple page sizes. If we increase the page size, say from 8 kilobytes to 32 kilobytes, we quadruple the TRB range. However, this may lead to an increase in fragmentation for some applications that do not require such a large page size. Alternatively, an operating system will provide several different page sizes. For example, the UltraSpark supports page size of 8 kilobytes, 64 kilobytes, 512 kilobytes, and 4 megabytes. Of these available page sizes, Solaris uses both 8 kilobytes and 4 megabytes page sizes, and with 64 entry TLB, the TLB range for Solaris ranges from 512 kilobytes with 8 kilobyte pages to 256 megabytes with 4 megabyte pages. For the majority of applications, providing support for multiple page sizes requires the operating system, not hardware, to manage the TLB. For example, one of the fields in a TLB entry must indicate the size of the page frame corresponding to the TLB entry. Managing the TLB in software and not hardware comes at a cost in performance. However, the increased head ratio and the TLB range offset the performance costs. Indeed, recent trends indicate a move toward software-managed TLBs and operating system support for multiple page sizes. Section 4. Inverted page tables. Last chapter, we introduced the concept of the inverted page table. The purpose of this form of page management is to reduce the amount of physical memory needed to track virtual to physical address translation. We accomplish this savings by creating a table that has one entry per page of physical memory indexed by a pair, precise identifier, and page number. Because the key information about which virtual memory page is stored in each physical frame, inverted page tables reduce the amount of physical memory needed to store this information. However, the inverted page table no longer contains complete information about the logical address space of a precise, and that information is required if a referenced page is not currently in memory. Demand paging requires this information to precise page faults. For the information to be available, an external page table must be kept. Each such table looks like the traditional per precise page table and contains information known where each virtual page is located. But do external page tables negate the utility of inverted page tables, since these tables are referenced only when a page fault occurs? They do not need to be available quickly. Instead, they are themselves paged in and out of memory as necessary. Unfortunately, a page fault may now cause the virtual memory manager to generate another page fault as it pages in the external page table. It needs to locate the virtual page on the backing store. This special case requires careful handling in the kernel and a delay in the page looking up processing. Section 5, Program Structures. Demand paging is designed to be transparent to the user program. In many cases, the user is completely unaware of the paged nature of memory. In other cases, however, system performance can be improved if the user has an awareness of the underlying demand paging. Let's look at an example. Assume that pages are 128 words in size. Consider a C program whose function is to initialize to 0 each element of a 128 by 128 array. The following code is typically. So this one. Notice that the array is stored row major. That is, the array is stored data 00, data 01, data 0127, then data 10, data 11. For pages of 128 words, each row takes one page. Thus, the preceding code zeros with word in each page, then another word in each page, and so on. If the operating system allocates fewer than 128 frames to the entire program, then its execution will result in 128 by 128 and equals to 16,384 page faults. So if we changed in contrast, suppose we change the code to this. This code zeros all the words on one page before starting the next page, reducing the number of page faults to 128. So careful selection of data structures and programming structures can increase locality and hence lower the page fault rate and the number of pages in the working site. For example, a stack has good locality, since a size is always made to the top. A hash table is designed to scatter references producing by the locality. I/O interlock. Pages must sometimes be locked into memory. So look at the example. A process P1 issues an I/O request and is put in a queue for that I/O device. The CPU is given to is scheduled to other processes. These processes cause page faults using a global replacement. One of them replaces the page containing the memory buffer for the waiting process. This one, okay? So when the I/O request of process 1 advances to the height of the device queue, the I/O occurs to the specified address here, but it has been changed. This frame is now being used for a different page belonging to another process. So solutions. Never to execute I/O to user memory. I/O takes place only between system memory and the I/O device. To write a block on a tape, we first copy the block to system memory and then write it to tape. Second solution. Pages that are used for copying a file to a device must be locked from being selected as victims by a page replacement algorithm. A lock bit is associated with each frame. When the I/O is complete, the pages are unlocked. Another use for a lock bait involves normal page replacement. Consider the following sequence of events. A low priority process faults. Selecting a replacement frame, the paging system reads the necessary page into memory, ready to continue. But the low priority process enters the ready queue and waits for the CPU. Since it is a low priority process, it may not be selected by the CPU scheduler for a time. While the low priority process waits, a high priority process faults. Looking for a replacement, the paging system sees a page that is in memory but has not been referenced or modified. It is the page that the low priority process just brought in. This page looks like a perfect replacement. It is clean and will now need to be written out, and it apparently has not been used for a long time. Whether the high priority process should be able to replace the low priority process is a policy decision. After all, we are simply delaying the low priority process for the benefit of the high priority process. However, we are wasting the effort spent to bring in the page for the low priority process. If we decide to prevent replacement of a newly brought in page until it can be used at least once, then we can use the lock bait to implement this mechanism. When a page is selected for replacement, its lock bait is turned on. It remains on until the faulting process is again dispatched. Using a lock bait can be dangerous. The lock bait may get turned on but never turned off. Should this situation occur because of a bug in the operating system, for example, the locked frame becomes unusable. On a single user system, the overuse of locking would hurt only the user doing the locking. Multi-user system must be less trusting of users. For instance, Solaris allows locking hints, but it is free to disregard these hints if the free frame pool becomes too small, or if an individual process requires that too many pages be